Good evening, everyone. On behalf of the Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore, I welcome all of you for the day 5 sessions. We have successfully completed day 4, and we are in day 5 session, and tomorrow we have one more session. With that, we are going to wind up this ATAL FDP. So I hope all the participants will join, and they'll also get benefit out of it. Kindly encourage your colleagues or friends. They are attending this FDP, ask them to join soon. So today's session will run from 6 p.m. to 9 p.m. I would like to read the instructions for the participants. There will be 2 sessions today, and only one feedback form needs to be filled today. The feedback link will be shared at the end of the session. Both sessions will be handled by one resource person today. So there is only one feedback form that will be shared at the end of the day 5 session. Kindly note down your participant ID as usual through your mail or from your WhatsApp. You can able to find out your participant ID since it is needed for filling your feedback form. For any technical queries, kindly post them in between the session in the chat box. And at the end of the session, you'll be given chance for raising your hand and you can unmute. You'll be unmuted and you can talk with the resource person and you can clear your doubts. I'd like to introduce the resource person. He's Dr. Aravind Vishnu. He is an academician as well as a researcher in the specialization of cryptography and cybersecurity. Currently, he is working as an assistant professor at TAFAC core in cybersecurity, Amrita Vishwa uh, Vidyapeetham, Coimbatore. He completed his PhD from Amrita Vishwa Vidyapeetham, Coimbatore. His doctoral research focuses on lattice-based cryptography, especially developing and analyzing IND to secure authenticated asymmetric encryption schemes. He has made notable contribution to his field through numerous journal articles as well as through conference papers. His research contribution includes developing a hybrid sign encryption method that combines elliptic curve pairings with the vector decomposition problem, for which he proved IND-CCA2 security in the random oracle model. He has also explored lossy trapdoor functions to assess the feasibility of post-quantum secure crypto systems and demonstrated the benefits of using spawn based hash functions in hybrid encryption schemes. Additionally, he employed lossy trapdoor functions based on the learning with the errors problem to construct a post-quantum secure asymmetric encryption with entity authentication, and conducted an in-depth security analysis of an aggregate sign encryption scheme based on fog computing. Dr. Aravind Vishnu will be sharing with us today on the topic cryptography in the quantum field. So the topic he's going to discuss about the first session, and the same topic he's going to continue in the second session as well. Welcome, sir. Now you can take over the session.
Thank you, ma'am. Thank you so much for the very nice introduction and the opportunity you are given to me. Hope I'm audible to everybody. Uh,
Yes, sir. Yes, sir.
Thank you so much. I'll be sharing my screen. Is my screen visible to you?
Yes, sir. Yes, sir. Your screen is visible. Do you want to enable your video?
Is it required, ma'am? If it is
Just
required,
for 1 or 2 minutes, sir.
yeah, sure, ma'am. Not an issue with that. But it'll be
Okay.
on two different panes. So I'm not sure if the thing, because I'm sharing it from two different systems. So
Okay.
that's why I
Okay.
just took my this thing off.
Okay. Okay. So, which is comfortable for you? Please go ahead with that.
Yes, ma'am. Sure, sure.
Okay. Thank you, sir. Thank
1 second, ma'am. So is it my face or the screen which is visible to you now?
you. Yes. Yes, sir. Yes, sir.
I mean, the screen is visible currently, right?
Yeah.
Okay,
Everything
so
is okay.
yeah, fine. So very fundamentally, let me start with the idea of cryptography. So we need this particular concept of cryptography in our daily lives. I don't know actually how many people have, or how many of the participants have actually heard of cryptography already, because this is kind of thing which we daily use. How many of you have noticed that one message when you open a new WhatsApp chat? This is end-to-end encrypted. Maybe, ma'am, can they unmute and talk, or like we'll keep it for the end? Can we make it interactive? Is it possible? You are muted, ma'am. I can't hear you. Ma'am, you are muted. I can't hear you. You are talking, but I can't hear you.
Yes. Yes. Sorry. Sorry. So they can click on a raise hand option in
Yeah,
the screen, and they I will unmute immediately.
sure, ma'am. Sure. Thank you. So, basically, the cryptography means securing your personal communication or securing your banking, securing your. There are multiple applications of cryptography which we come under in our daily life. Okay. So, I'll just give you a brief introduction, but let me just give you an introduction through the applications which we use regularly. So let us just focus on the necessity of cryptography. So let us consider the idea social media first of all. Most of you might be using WhatsApp, Facebook, Instagram, and many other social media handles to maybe publicize your work, publicize your life, or for multiple purposes. What if somebody gets access to these things? Maybe your credentials and all these things, maybe they can actually enable or enact as yourself to somebody of your knowns, so that they can actually masquerade as or fake as you and ask for money, demand them something, and actually you will be the one who is trapped. So social media password, social media protection, everything is actually protected, and we require cryptography to protect them. Then comes your banking. See, you have seen this one time password, two-time verification for authentication. Now we have this multiple kind of authentication checks in banking sector when you are doing internet banking and all, right? So when we are doing internet banking and all sort of things, we require strong privacy enforcing mechanisms which we ensure using cryptography. Similarly, other privacy ensuring mechanisms like maybe your social media is one example, banking, other maybe your personal chats, personal folders, drives, etc. should be personal to you. It should be with you only. And there are Wi-Fi security. Then, how many of you have noticed kind of a padlock symbol on top of the website? That if you click on that, you'll see the certificate thing and all those things. So all these things actually involve cryptography. And you might have heard of this thing called e-voting, which is predicted to be occurring in the future in our country also. But as of now, it's not available right now here. In foreign countries, it's available. So all these are the necessities which we are actually using in cryptography indirectly without knowing them that we are using. So cryptography is a necessity which we can't avoid. Suppose if you are not worried or concerned about your privacy, your money, your identity, your well-being, it's fine to you. You don't have to worry about cryptography. But otherwise, indirectly or directly, if you are not worrying about cryptography, we have to worry about cryptography because we ensure the safekeeping of your money, your social media, your banking, your privacy, etc. So, cryptography offers confidentiality, integrity, authenticity, and non repudiation. Whereas confidentiality means a message sent from a person to another person reaches the other person without being read or known to the person in the middle. That is what we mean by confidential. The information is confidential within the participating entities. Integrity. That is, when we send a message, the third person, even if he is not able to understand or interpret the message, he might tamper with the message. That is possible, right? So if you can't have it, just destroy it. That's the kind of attitude we have nowadays. So the integrity of the message, that is the we have to make sure that the message we send from one end is the one which is reached or which is reaching the other end. Now, authenticity. See, I'll give you a simple example of authenticity, like authentication or authenticity. Like, how can you make sure that I am the so-called Aravind Vishnu? You don't know me. Most of you, I mean, I think none of you might have seen me previously, other than from that poster. So, how will you authentic? I mean, how will you authenticate that, or how will you feel authenticated that I am the right person here? Because you have seen my face on the poster and you can match it with the video face which you already saw. So you may, so without that authentication mechanism, if I just showed you only my screen and not my face, will you be able to recognize that it's me? No, you won't be. It might be some person who is talking in on behalf of me, but might not be me. So this is the idea of authentication, which is actually important, which is very important. And non-repudiation is some kind of we call it as undeniability or non-deniability. Suppose we claim to have something, claim to own something, then we actually have to at the later point of time we should not be able to deny that fact. If I say I'll give you 10,000 rupees if you do something, and after the job is done, if I deny that I didn't say anything, that cannot be done. That is what is called non-repudiation. Now, we have types of cryptography in two ways, symmetric as well as asymmetric. In case of symmetric cryptography, what happens is, let us take a simple example of a padlock system. Let us consider a padlock with a maybe two keys. Padlock means normal lock. So if you consider that system, suppose you are two entities, you are communicating with another person who is actually having that particular spare key. Suppose, for example, I don't know anybody of you. So let me take the example of me as well as Carnegie University representative Dr.Jemima ma'am. Suppose we both are having one personal key which we used to communicate between ourselves. Then what I'll do is I'll put the message in a particular box. I'll lock it with the padlock where I'm having the key, and I'll send it to madam. She will only be able to open the padlock because she only has the spare key. So if we both are using the same key on either ends, it is kind of a symmetric operation. That is what we call symmetric cryptography or symmetric encryption, where both the parties are using the same key to encrypt or to read the messages, or for any operations on either sides, they'll be using the same key. And symmetric encryptions are actually very common in the sense like we are using it daily, starting from our WhatsApp, Telegram, whatnot, even iMessages, whatever. And message authentication is one another thing which is actually ensured by symmetric cryptography using message authentication codes, which is abbreviated as MACs. Now, some of the very well-known symmetric cryptographic schemes are AES, which is Advanced Encryption Standard, Cha-Cha-20, Two-Fish, etc. See, Advanced Encryption Standard is kind of a standard. It's not the name of the scheme, but there was a competition conducted by National Institute of Standards and Technologies in 1999 to identify the prominent symmetric crypto system, and many came up with the solutions. Out of which one cipher, which is known as the Ringdale cipher, proposed by Damon and Ridgman, they actually proposed one cipher called Ringdale cipher that came out to be the winner of the system or winner of the competition. And then we have announced, or they have announced, that Ringdale cipher from then onwards came to known as the Advanced Encryption Standard. Before that, it was DES, Data Encryption Standard. It was replaced by the Ringdale cipher as AES. Chacha 20 and Twofish are currently used actually in current applications nowadays. Anyway, now this is where we are more focused on, because I just gave the symmetric cryptography first because we are not going to focus too much on that, but we are focusing too much on asymmetric cryptography, where asymmetric cryptography is something where we use different keys at both the ends. We call it public key cryptography as well. I'll tell you another example for the same thing. If we have a same padlock example, we can keep. Suppose I want to send any one message to any of the participants, or suppose any of the participants want to send a message to me. Suppose I am keeping a spring padlock which can be locked using a just a click, which need to be opened with the key, but which does not require a key to close it. You can just click and close. So if you have such a system, such a maybe padlock and a box, I am keeping my box in a public place, and I'm keeping my padlock along with that inside. If you want to send me a message, what you will do is you will put the message in the box and you close the box and lock the padlock. Now, even if you think of opening it, you won't be, because opening the padlock requires the key, whereas closing it does not require anything but just a click. So now I am the only person who will be able to open that key legitimately. So the box will be sent to me, and I will be using that box or the key which is entitled for that box for the corresponding decryption, so called. Then I'll open the padlock, I'll open the box, then I'll take the message. That is how we it works in asymmetric cryptography if you want it in a real life scenario. Now, asymmetric cryptography is basically, obviously, you can imagine it's more expensive than classical or symmetric crypto systems. So, what we do is we need symmetric encryption key to be transported to the other person. We don't know the other person, but once the other person is authenticated and we trust him, we will actually share a symmetric encryption key with the other person. But for symmetric encryption key, we require some transporting mechanism. Asymmetric encryption key or public key encryption actually works as a symmetric key transport mechanism. So it's actually expensive, but only once we use it. So we use it only once to transport or exchange these symmetric keys between parties. Then we actually refrain from using asymmetric cryptography. We will switch to symmetric cryptography using the key we shared using the public key. Now, asymmetric cryptography's applications does not actually restrict or confine to encryption or key transfer. It actually can be used as a digital signature scheme. It can be used to authenticate entities to each other. It can be used as to create certificates and in hash functions. We are using our hash functions are part of asymmetric cryptography. Somebody of you might have heard of hash functions. If not, it's not a crime. It's fine. So, some of the examples of asymmetric crypto systems are RSA, Elgamal, Diffie-Hellman, elliptical cryptography, etc. Now, obviously, we have already discussed that they are different. So, what is the at least the minimal extent of difference which they have? That is, first of all, the keys. As I mentioned already, the keys are actually playing the important classification role. If they are having the same key on both sides, or the copy of the same key on both sides, we call it a symmetric encryption scheme. Whereas in the case where we have different keys on either sides, then we call it a asymmetric encryption scheme. Please don't feel worried whether we are talking about talking confined to quantum world, because I can't come directly to the quantum world without letting you have a very basic fundamental idea about what cryptography is. Otherwise, this will be a time waste for both of us. So please bear with me and listen. Second case is the hard problems. The hard problems are actually confined only to asymmetric crypto systems. Why? Because uh, in symmetric crypto systems, we engineer those things based on the iterations and the positioning and bit length, bit flipping, all those mechanisms and the techniques there. But the asymmetric crypto systems are actually based on mathematical hard problems. That is, if you want to break an asymmetric crypto systems or a public key crypto system, I can see some message over there. Let me check it once. Okay, it's actually confining to some other thing. Okay, fine. Okay, so back to the hard problems. So we actually have mathematical hard problems, um, which are actually paving the basement for asymmetric crypto systems. Like if you in general terms, actually, if you want to, like, it's like having a kind of bodyguard, not in exact fashion but analogically. So bodyguard says what, if you want to touch or do harm to my boss, you have to touch me. That is, hard problems actually says that if you want to break the crypto system, you have to break the corresponding hard problem. That is, you have to solve the hard problem. Or we have proved that solving a crypto system is actually equivalent to, or it's actually leading your way to solving the hard problem and on the whole. Now let us consider the idea of one-way and trapdoor functions. Okay, let me just put an example of one-way and trapdoor functions in the general setting. So basically, one-way function, by the name suggests, can be computed one way. That is, suppose I give you maybe a number, say 15 or 20. Let us say 20. How many I actually thought about two numbers in my mind, and I gave you the number 20, which is the sum of those two numbers which I thought. Can anybody comment on the chat box about what the numbers are? Any idea about those numbers? Anybody? Let us just make it a little bit interesting or interactive. So, I'm having this two numbers whose sum is 20. Can you get me those numbers which I was thinking of? Anybody? Yeah, we have a solution 10 plus 10. Anybody else? 12 and 8. Wonderful. So you can comment if you have options, but still, I got what I required. So we have options like 10 plus 10, 12 comma 8. So do we have a fixed answer for this question? Obviously, no. So that, see, both these answers are valid. You can see both these answers are valid. 10 plus 10 is valid and 12 plus 8 is equally valid. So, see, finding the number one way, I took two numbers in my mind and I just gave the sum of the numbers to you. I computed the outcome or output of the one-way function. That is, I took two numbers and I just added them and I just gave you the sum of the numbers. But now the catch is whether the person who received the numbers, that is you, who is on the other end, will you be able to guess the numbers? So going back from there has infinite number of possibilities. Is it not? What if I give you that one of my numbers is 22.8? What can be the numbers in this scenario? Can somebody comment on that again? The one number I thought of was 22.8. Yeah, we have multiple options from mm, to get the idea to get the value 20, but I am not talking about 22.8 as a sum. I'm telling you that the sum is 20 and one of the number is 22.8. It's not like 12.4 and 10.4. Like I get the point. So this is not what I tried to convey. The sum remains 20. Sum of two numbers a and b. I'm saying a plus b equal to 20 and a is equal to 22.8. So what will be my b? That's the question. If I say a plus b equal to 20 and a is 22.8, what will be my b? Simple thing. A plus b equal to 20. Exactly. B will be minus 2.8. So we have now, you guys were giving me different answers until this point, but you came into a unison or a agreement in this case where I gave you some information that one of the numbers is 22.8. So now you are saying that the other number is minus 2.8. So what does that mean? This means that you can actually get the complete information from partial information. So I didn't give you the numbers as such. I just gave you information about the sum, the process I did, and the one of the summands or one of the values. So this is what we call a trapdoor information. That is, using the trapdoor information, you will be able to identify the complete information. That is, from partial information, you will be able to understand the complete information. This is the beauty of one way and trapdoor functions, because until the trapdoor was given, this was a one way function, and when the trapdoor was taken or trapdoor was introduced to you, then you came to be giving me a single solution which is minus 2.8 or negative 2.8, which is the unique solution. Why? Because that's the only solution you can reach from the given information. So that is how we set the trapdoor function. So the process of doing one way functions and trapdoor functions, I think it's clear to you. Anyway, one of the examples which I wanted to tell you was the padlock examples. So you know that. And the another example is the mailbox example. So all of you are having your email IDs. All of you are from different organizations, or maybe let it go. Let us just not worry about the organization. You all are having their personal email IDs. Suppose somebody wants to communicate to you, they will be actually getting your email ID and sending you the message. So most of the mailing systems won't allow a message to be taken back if it is not Outlook and all. Maybe you won't be able to recall the message. So this acts as a analog to public key encryptions or public key system where we actually mail somebody, but the mailbox can be opened by the owner or the person who has access to the key of the mailbox. But who can send email? Whoever is available or whoever is seeing or whoever is getting access to the email IDs or email ID will be able to mail you, which means this is a public key encryption analogous scenario where any public person, that is anybody from the world, can email you, but only you can see the email once you open it. And the person who sent the email, considered in the case of a non recallable mailing system, you won't be able to call the mail back or make any modification to the mail once sent. That's the idea of a public key crypto system. I hope you get the very, at least a vague idea of public key crypto systems. Can you just comment yes or no, or like questions, anything? Let us just go small steps at one time, because that will be making the job easier and fruitful. So please comment if you have any comments, or like just put an yes if it is fine with you. Okay, thank you. Now it starts technical, so little bit mathematical also. So before we begin, let us have some formal definitions. These are the things which we need to know: group, cyclic group, generator, order of a group, order of an element, Euler phi function, integer factorization problem, and the discrete logarithm problem. These are the informations, or these are the paraphernalia or itineraries which we require before we just begin. So let us just start with the Euler's Toshin function or Euler's phi function. I hope everybody is familiar with the concept of GCD, the greatest common divisor. Let me put an example. Say GCD of 2 and 4 is 2. GCD of 4 and 6 is again 2. GCD of 6 and 9 is 3. So the greatest common divisor, it's a basic concept. I think everybody is aware of that. Please pardon me if I am, if you feel that I am mocking, but I just wanted to give you maximum clarity. I'm not trying to offend anybody. Please. Okay. So Euler-Toshin function says that for any number n as an input, Euler-Toshin functions gives the number of elements which are number of positive numbers, positive elements starting from 1, positive integers, less than that number, less than the given input n. And there actually we talk technically about the word coprime, which means GCD of a and n should be 1. That is, it actually collects all numbers and takes the outputs the number of elements or number of integers starting from 1 till the number n, not including n, which are having no common factors with n. For example, we can say phi of 5. 5 is a prime number, so all numbers less than 5, 1, 2, 3, and 4, are actually having a GCD 1 with 5 because they don't share any common factors. So phi of 5 will be 4. If you consider the phi of 6, n equal to 6, then in that case we have, if we take 1, 1 is having GCD 1 with 6, 2 is having GCD 2 with 6, so we can remove 2. 3 is having GCD 3 with 6, remove 3. 4 is having GCD 2 with 6, remove 4. And 5 is having GCD 1 with 6. So only two numbers are there which are less than 6 and coprime to 6. So phi of 6 will be 2. Now we have order of a modulo n, which is denoted by order of a to the base n. So for the integer values k, m, and n, and any number a coprime to n, we have only those numbers which are coprime to n will have the GCD, will have the order. So order of a to the base n is in is k. If a power k mod n is congruent to 1 modulo n, and no number less than k, no integer less than k, will give you a power m modulo n should be 1. So that is, it is the least positive integer k which gives you a power k congruent to 1 modulo m, or a power k mod n is equal to 1. Now let us set up the foundation basement from the next level. That is, we work on a specific application called a group. So G star, that is, group is a set with a binary operation which is actually having satisfying some of the properties. The properties are listed here. A set G with an operation star is a group if it satisfies the following properties. The properties are, first of all, closure, which says if two elements are belonging to the group, then their output of the binary operation, that is A star B, should also belong to G. Associativity, I mean, actually, I have missed something there. You should also say that B star A also should belong to G. That need not be the case always. Say, if I just put the case where maybe division, suppose operation star is division, suppose, then if I take 4 and 2, obviously 4 by 2 will be belong to the integers. Yes, but 2 over 4 is 1 by 2. That is B star A is 2 by 4. 2 by 4 is 1 by 2, which does not belong to the integer set. If my set of integers, if my G is the set of integers. So that is a case where the closure property should be applicable in both scenario A star B as well as B star A should be part of G. Anyway, division does not make any sets group, so we are not bothered about that. And associativity, that is for any A, B, and C belong to the set, A star of B star C should be A star B star C. That is, it should be associative. These are all common terms which anybody knows, I assume that. And there comes the existence of an identity. That is, there should be an element E in G such that A star E equal to E star A, which is equal to A. And for the final property, we call it as existence of inverse. That is, for every A in G, there exists another value B in G such that A star B equal to B star A equal to E, the identity. So order of a group, in contrast with the definition of order of an element, order of a group is the number of elements in the group. Quite simple. Any questions, anybody? I think we can move on. So another definition, which is a generator. A generator is actually an element G, part of the group G, which actually generates the whole group G or generates some elements, that is G, G square, G cube, etc. G power K generates some particular elements where K is the order of G. Why? Because this is the set generated by G. Why? Because G power K plus 1 will be equal to G again. Why? Because G power K, which we mentioned as from the definition of order, we have that G power K modulo N will be 1. That is, if K is the order of G, then G power K will be 1. So G power K plus 1 will definitely be G power K into G, where G power K is 1 and G will be G power K into G will be G again. Now, a cyclic group. Connecting to the generator, a cyclic group is a group which can be generated by a single generator. We can generate groups by having multiple generators, but this group, this particular type of group or cyclic group is actually one particular type of group which can be generated by a single element. That is what we call cyclic group. For example, let us take say integers under addition, collection of all integers under addition. So if I take the value, say 1, can I find all the, is it cyclic group? Is it a cyclic group? If I take 1, I can just 1 plus 1, 2, 1 plus 1 plus 1, 3, 1 plus 1 plus 1 plus 1, 4. Can I? Okay, we leave it to the listeners. So now back to the integer factorization problem. See, we actually started talking about asymmetric crypto systems, and these two are the very fundamental building blocks of an asymmetric crypto system. The integer factorization problem as well as the discrete logarithm problem. We needed, these are the two mathematical hard problems which paved the basement or which paved the fundamentals for the asymmetric crypto systems starting in the late 70s or early 80s. The integer factorization problem simply says given n is equal to pq, where p and q are two distinct prime numbers, you will be given n, but you have to find p and q. See, this might seem obvious or like silly for somebody, because suppose you might think, okay, what about 21? 21 is 3 times 7. What about 35? 5 times 7. What about say 91? 13 times 7. What about 105. Some you have factorization. But as the number gets larger, larger, and larger, this problem gets tough. Suppose I give you some numbers, say 2 to the power 2 to the power 7. That is 2 to the power 128 plus 1. Will you be able to identify whether that number is a prime number or not, or whether it has factors or not? It's not an easy task. I mean, will you be able to calculate 2 to the power 128 easily? Considering 2 to the power 10 is 4 digit, do you think that 2 to the power 128 is somewhere near some 5 6 digits? Obviously, it is not. So, if you are given numbers, prime numbers p and q, you have to multiply and give it out, the value n. Then, if a person who gets n is able to predict the values or calculate the values of p and q, your integer factorization problem is solved, that is tracted, and otherwise the problem stays strong. So you have to choose p and q so strong such that the n value is publicly available, and that value should not leak any information about the primes they are using. Another one is a discrete logarithm problem, which we are actually, for this problem only, we have learned the groups and cyclic groups. So suppose G generates the group ZP star, which is actually all numbers from 1, 2, 3, etc. up to P minus 1 under the operation multiplication modulo P. And H, which is our public key, H is equal to G power A modulo P. H is equal to G power A modulo P. Given the group information, the generated information, the prime number, and the H value, you have to find the secret value A, which is used to compute H from G. You can keep on multiplying G no matter what, but how long will you multiply? The number will be so big, so big that you won't even finish it in a decade going for brute force search. That is how discrete logarithm problem is set up. That is, given g, small g, p and h is equal to g power a mod p, you have to find the value a. Now let us step into the crypto systems. So let us start with the Diffie-Hellman key exchange. Let G be a multiplicative group modulo Q, which where Q is a prime number again. Let G be the group generated by the element small g, and n is equal to order of G. Suppose two participating entities. Anyway, I'm bored of classical Alice and Bob. Let us consider Anshuman and Barkha. Let us consider some indigenous names. So let Anshuman choose A randomly from uh, 1, 2, 3, etc. up to n minus 1. The notation is on the last portion of the slide. So square bracket n means the numbers from 1, 2, 3, etc. up to n minus 1. So you have to choose A randomly from 1, 2, 3, etc. up to n. Similarly, Barkha also chooses the same. Now, public key of Anshuman will be equal to G power A modulo Q. Similarly, public key of Barkha will be public key of B, pub B equal to G power B modulo Q. They will be exchanging their public keys similar to the discrete logarithm problem which you have seen. Given pub A and pub B publicly, you won't be, or the third person or anybody won't be able to get A or B values other than Anshuman and Barkha themselves because they chose them. So, pub A will be reaching Barkha and pub B will be reaching Anshuman. So, Anshuman will be computing pub B the whole power A, which is G power AB mod Q, and Barkha will be computing pub A the whole power B, which is G power AB mod Q again. So, they agreed on a common key called G power G to the power AB modulo Q. They have agreed on a common key G to the power AB modulo Q, but they haven't revealed any information about A or B, so they kept their secrets to themselves. So they let their public keys out and they agreed on a common key. This is what Diffie-Hellman key exchange or Diffie-Hellman key agreement says. So any questions on this? Anybody? I think we are good. So there are types of attack in the case of defilement, man in the middle attack, small subgroup attack. Then there are types of mitigation, which this part of the slide is for your later reference. So you may go back and, I mean, you will be given the slide, I think. You'll be provided with the slides, so you can go back and just look at that. If you are not given the slides, you can take a screenshot of it right now, and you can just learn more about these topics if you're interested. Now let us move on to the other crypto system, which is the prominent or well celebrated RSA crypto system, which is actually formed by the primes P and Q, where n is equal to PQ. So here in this crypto system, what we do is the security is obviously based on finding P and Q. So there will be two values E and D. That is why E and D means E represents the encryption exponent or encryption key, and D represents the decryption exponent or decryption key. So E and D are chosen or taken in such a way that E and D are actually inverses of each other, which means ED congruent to 1 modulo phi of n. Remember the definition of phi of n? Here we have ED congruent to 1 modulo phi of n. The ciphertext C, the encrypted message C, that is ciphertext C, which is encrypted as m to the power E mod n. That is the message to the power E modulo n. So we are powering the message with some number E, so that it actually changes shape to become C from the normal message M. Now that is the encryption part. After getting to doing the encryption, nobody knows about the decryption key. Only the key maker or the key holder knows the decryption key. So he will be finding C power D modulo n, which is uh, giving you the value m back. So again, this requires a kind of verification. If you require, just you can go through that later, or you can contact me over email. It's fine with anything is fine if you have a query on that. Now these are some conditions which we should ensure before choosing the numbers, that P and Q should not be so close, and the encryption or decryption exponent should not be too low also. And this is another variant of RSA crypto system using this Carmichael function lambda n. Instead of phi of n, that is p minus 1 into q minus 1, we will be using LCM of p and q, and we will be finding the same thing the same way. Instead of phi of n, we will be using lambda n. Now, you can see one thing here from this setting, that even if you encrypt, even if you, unless and until you change the key, you will be actually using the same key to encrypt a particular message time and again to produce the same ciphertext. That is, if you keep on encrypting it, the same message using the same key, you will be getting the same ciphertext time and again, which is not advised. This is called a deterministic encryption. That is, whenever or whoever or whatever person tries to encrypt the message M using the public key E, he will be sending the same C to the user. That is, even if person 1, person 2, or person 3 communicating, irrespective of who it is, if they are communicating using the same E, m power E mod n, that will be the same C value all of them are generating. And if they are sending the same C value to me, and if you intercept the communication in between, obviously the person who intercepts will come to know that this particular idea or this particular ciphertext which was sent was the same as the one which I sent already. So I will be able to guess the message or learn the message. Or the attacker who is watching from outside can guess that it's a common message, some kind of good morning, hi, bye, or all clear, something like that. He'll be able to get guess the values. So this is a problem. So you should not be having a deterministic encryption. So we'll see how to make it probabilistic later. Now, This is one phase or one particular idea, optimal asymmetric encryption padding, optimal asymmetric encryption padding, which was invented to randomize or make the RSA encryption probabilistic. What we mentioned was it was deterministic. Now we are saying that it is probabilistic. That is, given one particular message encrypted time and again, it will give rise to different ciphertexts. For before we start, we need two hash functions. Uh, we have a hash function g, which is converting a k0 length string to a k1 length string, and we have a hash function h converting k1 length string to k0 length string. Now the key generation phase will happen. PK and SK are the public key and the secret key. In our previous setting, it was E and D. Encryption will be M belong to an n-bit string. That is, message can be maximum an n-bit string, and we choose R randomly from a k-node. R is a randomly chosen k-node length string, or R is a string of size or length k-node chosen randomly from having component 0 and 1, or it's a binary string having length k0 chosen randomly. Now compute S such that M concatenated with k1 zeros. Actually, there's a typo. M concatenated with 0 so that the whole thing becomes k1. That's actually a typo. Uh, XORed with G of R. So G of R is depending on the input R, where the R is chosen randomly each time we do the message M. So even if you don't change the message M, the value R will be changing, and so is G of R. So G of R, when XORed with that concatenated or processed message, will give different S values. Similarly, T will give you, or T is calculated as R XORed with H of S, because R is having length K naught, and H is converting K1 bit string to K. S is a K1 length string, so it converts to K naught string, and they can XOR. Now encryption, you will encrypt using public key. We'll encrypt S and T using the public key PK and convert the value C, or obtain the value C. Now the C value is actually transported to the other end. So the decryption will be decryption of using the secret key SK of C, which is equal to S comma T. S comma T, which is obtained by, after decrypting C using SK, I'll be obtaining S comma T, where uh, what are S and T? S is actually, let us consider T first. I'll take T and I'll XOR T with H of S. Because I have S, I can find H of S. I'll XOR T with H of S and I'll be obtaining R. Now I'll be finding G of R and I'll be XORing that with M, and I'll be removing the last padded zeros, and I'll be getting back my message. This is how we do a probabilistic encryption based on RSA or any particular public key crypto system. Now comes another encryption scheme which is based on the discrete logarithm problem, which is called El-Gamal encryption scheme. So the El-Gamal encryption scheme has a different setting. It is not based on integer factorization problem, but it is based on discrete logarithm problem. That is, El-Gamal encryption scheme is based on discrete logarithm problem instead of integer factorization problem. So for discrete logarithm problem, we need a group which is cyclic, which means we need a group G modulo prime P, and let us consider small g be the generator of the group G. Let us again consider Q as the order of G. Let us consider the same example or same numbers as that of the one which we defined as in Diffie-Hellman. So for a randomly chosen X from 1, 2, 3, etc. up to Q minus 1, you can compute H equal to G power X modulo P, of which the information X is secret, and the information capital G, the group, the operation obviously, Q, which is order of G, the number of elements in G, and the small g, the generator, the H value, that is the public information that is computed by G power X modulo P. All these are sent as public. only keeping X as secret. So, as the definition or from the definition of the discrete logarithm problem, you might be learning that you might have learned that given all these information, you won't be able to understand or learn anything about X. Now, how to do the encryption? Embed the message to an element M in the group. You have to map your message M to some element in the group. Then choose a Y randomly from 1 to 3 etc. up to P minus 1. Then you have to compute S is equal to H power Y mod P. And you will be having two components of components in the ciphertext C1 and C2, where C1 is equal to G power the randomly chosen Y modulo P, and C2 is equal to M into S. Now, Anshuman, suppose Anshuman and Barkha are communicating using this particular thing. Anshuman is sending this particular C1, C2 to Barkha. Now, since G, small g, P and H are public, both Anshuman as well as Barkha knows the thing. So Anshuman is using only the publicly known information, not anywhere X. He is using capital G, small g, P and H only. Now Barkha, who is in possession of X value, will be finding S is equal to C1 power X, which is actually H to the power Y, because Barkha doesn't know about Y. She knows X. So C1 to the power X will be actually G power XY, which is same as C1 to the power X and H power Y, and finds S inverse mod P, or there are other ways of computing S inverse mod P, and computes M is equal to C2 into S inverse. So remember, C2 was M into S, and now there's a typo there again. CS, it's not CS but it's C2. So M is equal to C2 into S inverse, which is giving you C2, M into S inverse, which is giving you M back. So that is the idea of uh, Elgamal encryption scheme. So similarly, there is RSS signature where we can sign the message. That is, the RSS signature scheme actually gives you value or maybe authentication, because see, until now we were talking about encryption schemes where anybody in the public can access or send you messages. Now we are talking about signature schemes, where digital signature schemes where RSS signature is something which is formed by again primes P and Q. All the settings are the same, ed encryption decryption key is the same, but the only catch here is it's actually a signature which can be made or created only by the person who is in possession of the secret key. That is, anybody out there can verify your sign, but how many of you can create your sign? It is believed that, or ideally, it should be the case that only you should be able to, only you should be able to. The case is that only you should be able to um, get the. No idea. Only you should be able to sign the document, and anybody in the world can actually, if it is an authority, they'll be having some matching options. So they'll be matching it with the given or the sign. If it matches with the specimen, you can see, you have seen, you are signing checks, you are signing documents. So you know all those things. So if sign of M is equal to M power D, which is a secret information which is not only to me, will be leaked or will be put out, then any person who is having this value sign of M, that is M power D mod N, can verify by doing like sign of M to the whole power E, whether it is matching with M or not. If it is matching, then we are good. But given M power D mod N, they won't be able to find D or E. That's the idea. Now there are forgeries, types of forgeries, selective and existential. So selective forgery is actually getting the forged message on a selected signature, and existential forgery is some kind of mechanism where we forge messages from, or we forge signatures from already existing signatures. That is, let us consider the example, say sign of M1 and sign of M2 are there, signed using the same secret key. That is M1 power D and M2 power D, modulo N. If I want the sign on M1 M2, M1 into M2, I just have to do sign of M1 into sign of M2, right? Because M1 to the power D into M2 to the power D will be giving you M1 M2 the whole power D, which is again sine of M1 times sine of M2, which is sine of M1 M2. So that is one vulnerability or one existential forgery where we can forge signatures without having the proper signing key. Now we have another signature, algemal signature, which is uh, based on the discrete logarithm problem, which is having components like the previous case, but a little bit different. There will be a cyclic group ZP star, and let the space A equal to ZP star cross ZP minus 1. That is a signature space, which whereas the keys generated commonly as P, G, A and B, A and beta, where A is the secret information or the signing information, beta is equal to G power A modulo P. The signing key should be equal to A and the verification should be equal to P, G and beta. The algebraic signature is made in this fashion. The K is chosen randomly from Z P minus 1 star, which is equivalently saying that K should be coprime with P minus 1. Then gamma should be equal to G power K mod P, and delta should be equal to X minus A gamma, the whole into K inverse mod P minus 1. And sign on K will be gamma delta, where gamma is the second step and delta is in the third step. Now the verification happens like beta power gamma into gamma power delta should be equal to G power X modulo P. If you want to check, you can easily check, because gamma power delta will be G power K delta, and beta power gamma will be G power A gamma. So G power A gamma and G power K delta will be actually G power K delta. What does it mean by K delta? From the third step, you can see delta is equal to K inverse into something. So K delta will be X minus A gamma. So beta power gamma into gamma power delta will be G power A gamma into G power X minus A gamma, which is G power X modulo P. So if you have the value X with you, if you're having beta and the public key and gamma delta are given to you as signatures, so anybody on earth can verify whether these signatures are matching. So that is all. Before we continue or before we step into the quantum world, this is a brief introduction. Maybe we can take a break right now and we'll resume. Maybe Jemima ma'am, can we resume? When can we resume? Hello, Jemima ma'am. Am I not audible, ma'am? Hello.
Sir?
Ma'am, actually, we have finished the first part. Actually, I need more time for the second part. So can we just take a break and resume it a little bit early, by maybe like 15 minutes or 10 minutes break?
Yes, sir. 10 minutes break you can give. Participants, you can go for 10 minutes break and join after this. Okay, sir.
Okay, ma'am. Thank you.
Okay, thank you.
Hello, ma'am. Are we good to go?
Yes, sir. We can start. Participants, session 2 is started. Kindly stay back. Sir, please proceed.
Yes, ma'am.
Thank you.
So we are actually back to the session. We will be dealing with the topic cryptography in the quantum world too. Here is actually what we are more focused on the quantum and like why quantum and how what quantum can do. I was not part of the previous sessions which was handled here. uh, I apologize for not joining and not actually getting myself updated on what happened here. But I don't think anybody taught you about or anybody told you about the problems that can arise from quantum computing, did they? Can you comment on that, please? Anybody? Did anybody tell you about any like disadvantages of quantum computer in the last sessions which you have attended? Did anybody tell about the disadvantages of having a quantum computer? Not
Audience,
like
sorry, sir. Audience, kindly interact. If you press the raise hand option, I'll enable you to talk.
yeah. So I have this chat box open, so it's fine. If you can raise the hands and ask the questions, it will be wonderful. So now, so somebody is saying easy to hack the security system. Obviously, that is not a direct solution because hacking the security system. See, let me just since you gave me this idea, easy to I mean gave me this thought. I need to talk a little bit about that. Easy to hack the security system. See, we do hacking or some kind of intrusion only if the system is vulnerable or we use specific tools to get into the system. Okay, if a quantum computer is established, then we are not on the verge of some kind of hacking efficiency improvement or some kind of a drastic improvement and hacking efficiency won't be there. Why? Because the security system which you are talking about getting hacked requires to be weak. Then in the classical system also it will be hacked, or the software which should be developed from the scratch according to the logic of the system as well as the logic of the computer. They should be compatible and they should be written properly, and then hacking softwares are to be made and all those things should come up. Then only we will be able to hack the entire security system. So we are not looking forward to a system which can hack the system, but uh, anyway, we don't list that as an advantage of having a quantum computer anyway, not a hacking system. And somebody said it's not, and we have other options like higher error rate. Anyway, higher error rate is a disadvantage, but it's a disadvantage with the encoding or the computer. But having a the question was having a well fully furnished or fully equipped or fully compatible or fully usable or exploitable quantum computer, do we have a problem? So this is, this is what makes my topic or my discussion different from what the discussions happened already, because they were all talking about the advantages you are going to get when you are in a quantum world, that is you are having a good quantum computer. But I want to talk about the disadvantages of the quantum computer. So let us start with the, or this will be my content for the day, for the session. That is the quantum threat, the solution, which is post quantum cryptography, which is happening to be the cryptography coming after the quantum computers are established. We might think, but post quantum cryptography is already on. Now, the third one is quantum cryptography. I'll tell you the difference as we progress. Let us just put our focus to two important algorithms called Shor's algorithm and Grover's algorithm, of which Shor's algorithm is actually targeting um, what all one-way trapdoor functions based on integer factorization and discrete logarithm, which we discussed already. Grover's algorithm is a search algorithm which is actually reducing a search space in case of symmetric crypto system. That is, if you have a AES 128 which requires 2 power 128 brute forces, which can be done in 2 power 64 brute forces. That is, it is running in the big of square root of n time. That is the Grover's algorithm, but we are more focused on Shor's algorithm. And let me just give you a very crisp information or idea about how Shor's algorithm can work. So, Shor's algorithm does not attack directly on integer factorization problem or the discrete logarithm problem. It does not target and attack the DLP or IFP, which is the abbreviations of the discrete logarithm problem and the integer factorization problem directly, but it actually solves one problem called the order finding problem. See, Shor's algorithm solves the order finding problem. Now, what is the order finding problem? This is one case where we require the information about the order which we already talked about. So, we talked about the order of an element. I think you remember that we are talking about the order of an element. Order of an element is, let me just do a quick recall. Order of an element is the least positive integer k such that a power k congruent to 1 modulo p or n. So now let us consider the factoring algorithm. That is, we are going to factor value n be a semi prime. Semi prime means product of two prime numbers. So p into q equal to n is a semi prime number. Okay. Now let us choose a random number a from Zn. What do you mean by Zn? Zn is all numbers from 0, 1, 2, 3, etc. up to n minus 1. Let us choose a random number from Zn such that GCD of a and n is 1. Without loss of generality, let us assume GCD of a and n is 1. Why? Why? Because suppose we have GCD of a and n is not 1, then it will be either p or q. Why? Because n has only two factors, either p or q. So if the GCD of n and a is not 1, it will be either p or q. So we are actually on the solution, sitting on the solution of our concern or query, that is finding or solving the value for p and q. So if we are getting that, we are done, but that does not require quantum computer, right? So we are actually now bothered about a case where GCD of n and the chosen value of a does not have any common factors. That is, a is not a multiple of p, neither a multiple of p nor a multiple of q. Okay, let x belongs to Zn. Consider the following periodic function fx equal to ax mod n. So here we define a little bit about the period. There exists smallest positive integer r called the period of f such that f of 0 equal to f of r equal to 1. That is a periodic function which is repeating after a point of time. Further, assume f is strongly periodic, that is f of x1 equal to f of x2 if and only if x1 and x2 differ by some multiple of the period. Then R is precisely the order of element A in the multiplicative group n, group mod n. The formulation of finding period of f is used throughout our work. We just We'll just use that in our presentation. The shows algorithm is actually having a integer shows algorithm for integer factorization problem is or can be classified into three parts. The first part is classical, quantum, and classical, referring to the system requirements or the paraphernalia requirements, where in the first phase we will be requiring only classical bits or classical computer, which is our regular usable computer, and on the second phase we will be requiring a quantum computer, stable, error free or minimal error quantum computer, and the third one again a classical computer, which is our regular computer. So the first classical portion, so we'll use Euclid's algorithm to find GCD of the numbers. Let us consider n is odd and not a prime power, because n is mostly p into q, so we are only worried about that. And if n is a even number, again n can be made odd by removing the factors of 2 from that, so that's obvious. And for finding prime, factoring prime powers, we have other easy methods, so we are worried about only those numbers which are not even and not prime powers. So how does this work? That's the question. So how does this work? So let A randomly chosen from integers such that 2 less than or equal to A less than n. That is, A is a number between 2 and n. See, in the previous case, we were looking at the numbers from 0 to n minus 1. Here we are looking at from the numbers from 2 to n minus 1, both inclusive, such that GCD of A and N should be equal to 1. So again, the same idea. If GCD of A and N is greater than 1, definitely it can be either P or Q, where we are actually standing on our solution P and Q. So we are done with that. So GCD of A and N should be 1, which implies A belongs to Zn star. That is, A has a inverse and A has an order. So there exists R such that A power R congruent to 1 mod n, A has an order. Okay. Now we reduced this particular integer factorization problem to an order finding problem. Let us consider a value A which is having a GCD 1 with n. Now we are using the quantum algorithm, shows algorithm, to find the order of the given value A modulo n. So that is what we are going to find. So that is what the quantum portion means. Again, I'm not going to explain too much on the quantum portion. We'll be dealing with the classical portion again, because as of now, that is a tough pill to swallow. So back to the classical thing again. Suppose n divides a to the power r minus 1, which implies definitely if r is even, we have a to the power r can be, or r minus 1 can be split into a to the power r by 2 minus 1 into a to the power r by 2 plus 1. The same simple logic, a square minus b square will be equal to uh, a plus b into a minus b. So let us consider without loss of generality that R is even. If not, don't worry about that. Choose a different A. Start from the first. Check for GCD. Back to the quantum order finding. If it is an even number, proceed, or else choose a different A. Keep on doing that. Now, n divides a to the power r by 2 minus 1. Is it true? Definitely it cannot be true, because I told you that order of an element A is the smallest, least positive integer r such that a to the power r congruent to 1 modulo n. But if n divides a to the power r by 2 minus 1, it means that a to the power r by 2 will be congruent to 1 modulo n, violating our condition that r is our order. That is, there is this number r by 2 which is smaller than r, which is giving you 1, which is not possible, since the definition says r is the least number such that a to the power r congruent to 1 modulo n. Now, what happens? So, we have n divides the product of two values, of which n does not divide one value. a to the power r by 2 minus 1. So if n divides a to the power r by 2 plus 1, are we good? See, this is one classical example of a mathematical problem where we are doomed, or we are actually missed, or we are actually in a situation or a tough situation where we have a solution. The condition or the idea is n should not divide both a to the power r by 2 minus 1 as well as a to the power r by 2 plus 1. Why? We are not looking forward to a solution, we are looking forward to a factor. So what if P divides a to the power r by 2 minus 1 and Q divides a to the power r by 2 plus 1, or vice versa, that is Q divides a to the power r by 2 minus 1 and P divides a to the r by 2 plus 1, then n will not divide individually both a to the power r by 2 minus 1 or a to the power r by 2 plus 1, but n will divide the whole product because P and Q divides individually each of these values. But the catch is what? Suppose that n divides this thing. Obviously n divides, and suppose that n does not divide a to the power r by 2 minus 1, which means either P or Q should divide a to the r by 2 plus 1. So find the GCD of a to the r by 2 plus 1 and n. There you will get the value of one prime number. Without loss of generality, let us consider P. The other number can be n by P, which is Q. So this is how we use shows algorithm to find or to solve the integer factorization problem. This is how we tackle that situation. Now, for the hidden subgroup problem, that is for the discrete logarithm case, we will be using another problem which is solvable by shows algorithm, which is called the hidden subgroup problem. The hidden subgroup problem states that given a group G, H is a subgroup of G and a set X. A function f from G to the set X hides the subgroup H if for G1 and G2 belongs to the group G, f of G1 equal to f of G2 implies G1H equal to G2H. That is, in simple terms, if you have learned about the cosets generated by the subgroup H, the function f should be constant on same cosets and it should be different on different cosets. So f should be hiding H. We call f should be hiding H. So that is how we define a hidden subgroup, and the problem is to find a generating set for H or find H. I mean, if you have a generating set for H, definitely you will have H. Now, when X is a group and F is a group homomorphism, H corresponds to the kernel of F. Now, how will we connect this to the discrete logarithm problem? That is what we are going to discuss now. Let capital G, the group is a cyclic group generated by small g, and let X is equal to G power R modulo P. Then consider the function from ZP cross ZP to GB. Given random number f of AB equal to G power A into X power minus B. Okay, we are supposed to find R value. We are given X. We know X. So we are given any random value G power AB, f of AB equal to G power A into X power minus B. Given the function f is a homomorphism clearly with the kernel being generated by r comma 1, that is G power R into X power minus 1, that is we are having X is equal to G power R, right? So G power R into X power minus 1, that is G power R into G power minus R, which will be 1. That is, if the kernel is generated by R comma 1, then the value of f of AB will be 1, which is, since G is a multiplicative group, the identity will be 1, and all the numbers which are mapped to the identity will be inside the kernel. So kernel will be generated by R comma 1. So there are quantum algorithms, definitely the derivatives of shows algorithm or directly shows algorithm to solve the hidden subgroup problem, maybe to find the kernel. So the algorithm works like finding the kernel. So if they find the kernel, then the kernel will be actually, the generator of the kernel will be the uh, required value, because we are looking forward to the value of R. The first component of the kernel will be your secret value R. This is how we solve the discrete logarithm problem using Shaw's algorithm. Because see, until now, I don't even know if you realize the threat. So the threat is that you are actually forsaking all your privacy once the quantum computer is here. The quantum computer, see, the idea is, or the observation is, that once the quantum computer is available, it will be available with the powerful. It will be available with the rich. It will be available with the authorities. It won't be made available to the common man as and when it is made available or made stable. So the quantum computer, once they are published, or once they are made, or once they are furnished, or once they are, like, say, commissioned, that won't be available readily to any human, normal, regular person, but only with the authorities, and they will be actually trying to enter into your personal or secret life using the information provided. Or there is a saying in cryptography world which is called harvest now and decrypt later. That is, people will be keeping, or like, intercepting your messages and storing the communication in a separate channel, so that at a later point of time, when these quantum computers are there, the authorities can actually decrypt and see what you have sent on a previous date. So these are all the problems or issues which can arise when you are dealing with a stable quantum computer with the authority. Now, we have to find a solution to the quantum threat. Now, what are solutions to the quantum threat? The solution to the quantum threats are in two ways. Either find algorithms which the quantum computer cannot tackle, or switch to algorithms which are based on quantum computer, which are focused on quantum computer, which is nearly impossible as we don't have quantum computers readily available with us. So the only option which is available to us is switch to algorithms which are intractable even for a quantum computer. That is what we are going to do. But is it, do you think it is not time yet? If somebody of you are thinking that it is not time yet, think of it in such a way that, see, once the quantum computers are established and you started to lose the soil under your feet, there is no point in crying or running. So start early, develop your crypto systems, and switch to the proper safe crypto systems even way before the quantum computers are established. Because once you start your regular communications track in a post quantum secure or quantum secure communication channel, or a quantum secure algorithms are being used, or then you can switch to the previous encryptions can be re-encrypted or decrypted and encrypted again using the new algorithms as per convenience, maybe, so that they won't be actually further leaked. The already collected messages will be definitely leaked. We can't do anything, but we can prevent the upcoming communications which might be having potential leaking possibility or harming possibility can be prevented. Now, how do we do this? So reduction from integer factorization to order finding. That is what Shaw's algorithm do, and we have a quantum algorithm for order finding. So the idea for approaching this problem is in such a way that the quantum computers are actually targeting the order finding problem. So what if there is a hard problem, mathematical hard problem, which is actually not connected to the order finding problem, or which cannot be directly connected to the order finding problem? If we have such an algorithm or such a setup, then we are actually through from Shaw's algorithm alone. If there is a quantum algorithm which can do brute force on that, we are actually doomed again. But still, as of now, we have only Shaw's algorithms and the derivatives of Shaw's algorithm. So we are actually kind of safe if we can find or identify a research problem or a mathematical hard problem which is hard, obviously, and which cannot be converted to an order finding problem. Now, the solutions, as I already mentioned, we have two solutions, the quantum cryptography and post quantum cryptography. Obviously, post quantum cryptography refers to the cryptography in the world where quantum computers are established and are stably working. But it is not the post quantum cryptography after, only after the establishment of quantum computers. It is obviously the cryptography beyond this, but we have to start now at this point. And then comes quantum cryptography, which is the cryptography employed on quantum computers, which is entirely different from classical or cryptography or post quantum cryptography, because they are not same. People are thinking, or people use the word interchangeably with post quantum cryptography and quantum cryptography. They think they are the same. So quantum cryptography is not same as post quantum cryptography, as post quantum cryptography is a type of cryptography which is implementable on your regular computers or mobile devices or edge devices or any kind of communication devices wherever security is required, and you have been using it throughout until now. And quantum cryptography is something which can be employed only on a quantum computer, which none of us has access to as of now. Now, these are some of the post quantum cryptographic schemes or encryption schemes or key encapsulation mechanisms or signature schemes. Recently, not recently, from 2017 onwards, again, National Institute of Standards and Technologies, those who are listening from the first might know this particular idea about AES, the Advanced Encryption Standard. We were talking about AES and all those NIST and standards and all those things. So NIST has conducted a competition for post quantum standard, and they actually received multiple candidates, out of which most of the schemes were actually from the four hard problems or the four areas of hard problems, which are lattices, error correcting codes or error control codes, hash, and multivariate quadratic equations cryptography. So these are the four types of prominent cryptography. There is one another thing called isogeny based cryptography or super singular isogeny based cryptography, which is all equally important. But the problem is that there is actually an attack recently surfaced, not recently, like a couple of years ago. Castrick and Decru devised an attack to attack isogeny based crypto systems. So isogeny based crypto systems are currently not being used. These lattice based crypto systems, code based crypto systems, and hash based crypto systems are actually, and multivariate quadratic crypto systems are actually competed, and they were actually able to find a finalist, which is Crystal Skyber, which is a KEM, key encapsulation mechanism. But they still are actually continuing the competition. They still have a standard. Crystal is a standard, Kyber is a standard, but they still actually look forward to multiple or other options, because we are not sure, or we are not actually fully aware of what a quantum computer can do. So lattice-based cryptography involves basically Crystal Kyber or NTRU kind of crypto systems, and code-based cryptography involves Machilis, classic Machilis hidden Gopa code-based public key encryption system, which was an old system which is actually brushed up, and which was actually established first in 1978 but rejected due to the heavy key size. Now they are actually again surfaced it, and they are actually optimized it, and maybe still they are having a heavy key size compared to lattices. Now, hash-based crypto systems are actually based on hash functions, which are not prominent as compared to the first two. And then comes Petarin's HFE, new public key signing um, signature system, which is based on a multivariate quadratic equations. So these are the prominent crypto systems in the post-quantum cryptography, of which we are focusing mostly or fundamentally on lattices. See, we can't do everything together, so we'll just focus on the. See, since most of the NISC submissions were lattice based, we will actually focus on fundamentals of lattices. So a lattice L is a subset of Rn. Hope you all know what Rn is. Rn is the normal regular Euclidean plane, R cross R cross R n times the geometric figure which you already know, the n dimensional plane for n belongs to some positive integer satisfying the following conditions. There exists a constant c greater than 0 such that for all v1 v2 in L with v1 not equal to v2, the length or the norm between v1 and v2, norm of v1 minus v2, or the distance between v1 and v2 should be greater than c. That is, this should be discrete. They should not be continuous. If you take any random given lattice points, they should be having a minimal distance between them. So that is one idea about lattices. And lattice is an additive group. See, I think you all remember the definition of a group which we mentioned already. So additive group means a group G which is having addition plus as an operation, the binary operation. So L is an additive group. If you can just simply verify, if you take two vectors from Rn and you just add them component wise, you will definitely get another vector in Rn. And similarly, if you just do vector a1 plus a2 plus a3 will be the same as vector a1 plus the vector a2 plus a3. So it's all the same. So we don't have to worry about associativity, and the identity will be the all zero vector which is belonging to Rn. All zero vector will be the identity because a1 plus zero vector will be a1 again, and zero vector plus a1 will be again a1. And the inverse of any given a vector will be the minus a vector, where the components of a vector will be all taken negative. So you will be having that a plus minus a will be giving you zero vector. So this will be a additive group. So definitely this is an additive group. Now this is a additive discrete group, so that'll be too much mathematical if I talk about discrete topology, and also we just skip that part and we'll just move to the additional definition or alternate definition. So a k dimensional lattice is a set which is summation I equal to 1 to k xi bi, where bi's are linearly independent vectors belonging to Rn. There's something missing there. Bis should be linearly independent and xi belong to z. That is, we are taking integer linear combinations of linearly independent vectors belonging to Rn, and that will make it a lattice. See, you might be thinking about vector spaces, somebody. I don't wrong you, because definitely you can think about vector spaces that is so identical to this definition, but the only difference is that the value of xi's are taken from a field like real numbers or something like that, which is continuous. Here we are taking only xi's from integers. That is, will be only taking integer linear combinations of these values, so that this stays a discrete additive group. So a basis, I told you already that we will be dealing with some kind of vector space based applications, or kind of options which are connected to vector spaces. See, the two basic fundamental definitions which comes to our mind when we are talking about a vector space is, obviously, one is the basis and the second is the dimension. So similar to vector spaces, lattices also have something called a basis and a dimension. So the basis of a lattice is clearly the set B, which is B1, B2, etc., Bk, which is linearly independent and which is used to generate the lattice L. Remember, I use the term generate deliberately, because in vector spaces scenario we use the word called span. A basis vectors, or the collection of basis, or the basis or the collection of basis vectors, spans the vector space. That's the terminology used in case of the linear, I mean, in the case of vector spaces. But in our cases, in lattices, we don't use the word span, but we use the word generate. Why? Because we are not taking elements from a field, but we are taking elements from a ring which is integers. That is, we are taking only integer linear combinations b1 b2. So the summation ai, summation xi bi, where xi belongs to integers, will actually give you some kind of a value which is some kind of a set which is actually discrete. So it's actually in vector terms. We can write b dot zk, z power k, which is obviously the same as the previous definition. So the dimension of the lattice will be the number of basis elements, which is exactly the same as the vector space. We don't have to do any changes on that. But for basis definition, we have to make a small modification on the definition of vector spaces from here. So let us look at some examples of lattices. So integers are actually lattices on a real line. So when I talked about Rn can be R1 also. R1 is normally R. So R is the regular real number space or real number system. Real number system is having the subspace or subset or subgroup integers. So integers is a subset of subgroup of R, which is again a lattice, and any multiple of integers will be a lattice. The set of Gaussian integers, that is the numbers of the form a plus ib, which is geometrically equivalent to the vectors a comma b in R2, which in which a and b are integers, will be another example of a lattice. So this is geometry equivalent to Z2 over R2. This is one example which you can see. I am actually showing you only the first quadrant of the thing. I'm not showing the other quadrants. So the basis vectors here are, can you see, can you spot the basis vectors? The basis vectors are, we have seen one quadrant of R2. So can you comment what are the basis vectors here of the lattices, of the lattice, the quotient is Z of I or Z2 over R2? From the figure, are you able to identify the basis vectors? You can comment or you can just raise your hands. Anything is fine. Just let me know if you can give me an example, give me identify the basis vectors from the given figure. Okay, we still don't have an answer. Anybody? I mean, I just ask you to identify a basis or a basis element from the given figure. So I have given you the figure, it's already marked there. Exactly. So thank you. Thank you so much. Somebody has answered 0, 1 and 1, 0 is a basis vector for the given same basis, given lattice. Now, I have given another, I have marked another vector 1, 2, comma 2, 2. Do you feel that the same vector 1, 2, comma 2, 2 will generate the same lattice? What will be the lattice generated by the vectors 1, 2 and 2, 2? Uh, how many? Can you comment whether it's same or different? Just comment same or different. Okay. Somebody has mentioned it is same. Anybody feeling it's different? Basic linear algebra, so you can just simply look at it and say, yeah, we have multiple answers that they're all saying same. So see, the basic instinct to go for the shortest or easiest basis. See, in the first instances, you might not even have thought of that value 1, 2, and 2, 2 as a basis vector. Why? Because they don't actually look like or they don't actually seem to be a basis vector. So, this is where the hard problem comes. Um, see, will you please change time for online test because at that time we are going to home from college. Okay, ma'am, that question is for you.
Yes,
Sorry.
sir. I will address it at the
Yeah, I
end
mean,
of
I
this.
was looking for the comments on my response to my comments. So,
Yes.
please, participants, please stick to the thing, or you can have your queries addressed before the session or after the session, because you are not going from home, college to home, all of a sudden from 6 to 9. So, please let me have this thing here. So, Dr. Prashanti Aindala, like somebody is raising their hands, so can we just let her speak? I have seen her.
Yes, sir. I have asked her to unmute.
Yes, please.
I have enabled.
Dr. Prashanti, you may speak, please. Dr. Prashanti, you're all we are all yes. Please speak up. Like, what is the query? What is the question?
Ma'am, you have to unmute from your end. Okay, sir. You can skip.
Okay, that might be a
Yes.
like okay, it's fine. Again, Somdeep Sinha. So again, excuse me again. So please use this webinar chat only for responding to the comments, since you are not opening up. So please, again, back to the problem. So I have given you the vectors 1 2 and 2 2, and 0 1 and 1 0. Both are generating the same thing. But what happens here? See, look at the idea. This seems to be a very evident thing after we perceive it in such a manner, but in the initial stages, when just I gave you the figure, 0 1 and 1 0 were the obvious choice, and the other one was never a choice. But this is where the picture of easy basis and hard basis come. So 0 1 1 0 is a standard basis, which is easy basis, and 1 2 2 2 is a hard basis. So from there, if I give you only the basis 1 2 comma 2 2, so you won't be able to identify that, right? Maybe. Can you? Will you be able to identify that matrix? Will you be? So if I give you any random unimodular matrix, that will generate this particular thing. Like, say, let us say some example involving bigger numbers also. So you can just look at that number, like say 4 5 comma 5 5. Will that give you that? Okay, anyways, any number which you feel important, like say there's a vector, say 17 comma 10 3 comma, sorry, 17 comma 10 5 comma 3, which is actually giving you again 17 comma 10 and 5 comma 3 will give you a vector which is the same as this particular thing, which is actually having a different basis but a hard basis, which normally when we are looking at it, we won't even think like this is happening here. Again, next, uh, we have another definition called fundamental parallelepiped, which is the definition. By definition, P of B is equal to B dot minus 1 by 2 to 1 by 2, the left side inclusive, the power n, which is defined to be summation lambda I bi, where lambda I is ranging from minus 1 by 2 to 1 by 2, which can be any number from minus 1 by 2 to 1 by 2, not only integers. Let us look at some examples. So this will be the fundamental parallelepiped, which is there. That is, this is one fundamental parallelepiped generated by the basis, and obviously this is the fundamental parallelepiped generated by the other basis. So the fundamental parallelepiped changes, but the lattices won't change. Lattices are the same. So you will actually not identify the change in basis for the same lattice from the fundamental parallelepiped, but we use this fundamental parallelepiped for other purposes. Anyways, let us consider a unimodular matrix. A unimodular matrix U is a matrix which is having obviously invertible. It's a square matrix and cross matrix which is invertible, and the determinant of it should be 1 plus or minus 1. It's actually missing there. So again, apologies for the typo. A matrix U in Z cross Z n cross n is unimodular if and only if it's invertible, and it should be having a determinant plus or minus 1. So let b1 and b2 are two bases. Like in this case, we have 1, 2 and 1, 1. If you take 1, 0, 0, 1, that's the identity matrix 1, 2, 1, 1, which is giving you another basis, which is an invertible matrix. Obviously 1, 2 and 1, 1 are linearly independent, so that's an invertible matrix. And if you take the determinant, you will get minus 1. So you know that this is a unimodal matrix which is having an inverse, obviously, which can be transformed to 1, 0, 0, 1. Similarly, the examples which I gave, 17 comma 5 3 comma 10, sorry, 17 comma 5 10 comma 3. So which will give you actually the determinant 17 into 3 minus 5 into 10, which is giving you 1. So 17, that's a unimodal matrix again. So this is one classical example of a unimodal matrix. Another one which is not giving away any clue about it is generating this same lattice, which is generated by 0, 1 and 1, 0. Now, let us just simply move on to the hard problems, or move on to the cryptography part. The ith successive minima or nth successive minima. Let L be a lattice of rank n. Rank n means, what do you mean by rank n? Size of, we have done the definitions like basis, dimension, etc. So, a matrix of rank n is, so lattice of rank n is where that lattice is embedded in. That is, if it is a subset of Rn, then we call it as a rank n only if we have linearly independent, there will be n linearly independent basis vectors inside that particular lattice. So for I in values 1 to n 1, 1 to n minus 1, we define the ith successive minima as lambda I of L is the infimum of R, such that the dimension of span of L intersection the closed ball centered at 0 with radius R is having a value greater than or equal to I. Let us just skip this and do look at the example here. Let us come back later. So let us consider a lattice generated by the vectors 1, 0 and 0, comma 2.02. The vectors are 1, 0 and 0, comma 2.02. So this is a lattice generated by the vectors 1 and 2.02. So there will be only one linearly independent vector inside the ball of closed ball of radius 1 centered at 0, and that is the smallest radius where you can find a linearly independent vector, because if you just go less than 1, you won't be able to find any vector there, any lattice vector there. So you will have to go till 1 to find. You can go beyond 1, but 1 is the infimum value or the minimum value. But if you go to find the next successive minima, that is second successive minimum, you will have to expand your value or increase your value of R. You can go from R from 1 to 1.5, still only one vector is there. Again 1 to 1.7, 1.5 to 1.7, still one vector is there. 1.7 to 2, still one vector is there. If you go to 2 to 2.5, you will be finding two linearly independent vectors. Now you have to cut down from 2.5 to 2.3, still two are there. 2.3 to 2.1, still two are there. So that is the infimum value. 2.02 will be the least value where you can find a combination of two linearly independent lattice vectors within the ball of radius 2.02 centered at 0. That is the definition which is here, where B closure 0 R says the closed ball or denotes the closed ball of radius R centered at 0, which is collection of all values x such that norm of x is less than or equal to R if you want it mathematically. Now, let us look at some hard problems mathematically. Okay, we have some question here. As per the classical definition, there must be the existence of greatest lower bound and least upper bound for any two elements in the set. Similarly, can we talk about GLB and LUB in the lattice which is generated by linear combination of vectors? Obviously, we are talking about shortest vectors, but we are not worried about the largest vectors. So, obviously, your question is valid, but when we are talking about lattice vectors, the question about putting a bound does not matter. But when we are talking about the length of the lattice vector, that is, let us discuss the case of this decisional CVP and all, the decisional SVP and all, then in that case we will be addressing the same thing about the greatest lower bound or least upper bound as per the requirement. So if you are worried about the vectors, definitely the vectors is some kind of a multidimensional quantity, and GLB and LUB are kind of numbers, so they are not actually directly connected, but they are connected when we are talking about the length of the vectors. Let us consider that case. Let us look at the shortest vector problem, and when we are doing at the decisional vector, I'll just consider your I'll try to connect your query to the scenario. Now, connecting to the thing, lattice had problems, the shortest vector problem. So there are three variants of the shortest vector problem which are defined as follows. The first one is search SVP, that is given a lattice basis B. You should be finding the shortest vector. See, we have seen the definition for ith successive minima. The first successive minima will be the length of the shortest vector, which is obviously the infimum value of the or length of the shortest vector, which is the lambda 1 or the first successive minima of L of B. So given a lattice basis B, obviously I'll be giving you the hard basis, not the easy basis, because given the easy basis you will be easily finding that. Given the hard basis, see, same example, see, suppose I give you 17 comma 5 10 comma 3, sorry, 17 5 comma 10 10 3, you won't be able to identify that the shortest vector is 1 unless you perform some operations, right? So I'll be giving you maximum hard basis, and you will be asked to find the shortest vector from the lattice. That is the given question. Find the shortest vector. In our case, it was two vectors, 0 1 or 1 0. There were two lattice short vectors. But anyway, that is the case. Second thing is, second option is optimization SVP. That is, given a lattice basis, optimization version of the shortest vector problem, given a lattice basis B in Z m cross n, find lambda 1 of L of B. That is, you don't have to worry about finding the shortest vector. You have to just at least find the length of the shortest vector. We are only worried about finding the length of the shortest vector. And the third and final one, the decisional L SVP, given a lattice basis B in Z m cross n and R in rationals, determine whether lambda 1 of L of B, that is the length of the shortest vector, is less than or equal to R or not. Given two values, the basis as well as given two information about the basis as well as a random R. So will you be able to identify the shorter, see, please, this is a request to Mr. B Mahesh. So you can get the feedback form at the end of the session. Please don't disturb the session, because I'm actually looking at the comments of the people who are actually participating. Please don't spoil the thing. I request, this is a humble request, please consider. So decisional SVP, given a lattice basis B from Zm cross n, we have to find a value, or given an R, we have to determine whether the given from the given basis, whether the length of the shortest vector is less than or equal to R or not. So obviously, seemingly, we have the first problem is harder than the second, which is harder than the third. But to the surprise, every problem in this setting are equally hard. That is, there are options from, if you have a solution to the third one, there are ways to find the solution to the second one from the third. And if you have the solution to the second one, there are ways to find the first one from there also. So there are actually options here for us, which is saying that these three problems are equally hard. Now, considering the previous question from the participant side, in the last portion, if we are aware about the bounds of the shortest vector, then the last question can be answered. The length, if you are having some idea about, suppose you know about the greatest lower bound or the LUB, least upper bound, where it can be, then if we give a particular random number R chosen randomly from the rationals, we can just go and check whether that is actually compare that value with the greatest lower bound and the least upper bound or whatever quantity is available, and we may be able to get a solution, which actually spoils the problem. So this information is actually vital, which will not be available in a normal setting. Now, seemingly very simple thing, but a small change. The closest vector problem. In the previous scenario, we were actually worried about the shortest vector in a lattice, and now we are actually worried about the vector which is closest to a target vector in the lattice. That is, here we won't be given a here we will be given a target vector from anywhere in Rn, and we have to output with a vector, lattice vector, which is closest to the given target vector. See, SVP is a case of CVP. Maybe you can consider it as where the target vector is 0. Maybe. But it's not developed as a special case, but it was developed independently. Now, the same as optimization CVP, given a lattice basis B and a target vector T, you have to find the distance between, the shortest distance between the vector T and the lattice. That is, you have to find how far is the closest lattice point from the given target vector T. Now, the decisional CVP given a lattice basis B from Z M cross N and R belong to rationals, same as the previous case, determine whether the distance of the target vector and the lattice is less than or equal to R or not. It's the same. So these are the hard problems, some of the hard problems which are having approximate versions also. So for SVP, there are approximate versions where we don't have to find the shortest vector. We have to find a vector which is at least having a norm at least less than or equal to gamma times the length of the shortest vector. Similarly, the optimization SVP, we call it as gap SVP gamma, where given a lattice basis B, find a value D such that the value of the first successive minima or the length of the shortest vector lies between D and gamma times D. That is the optimization gap SVP, optimization of the approximate SVP. Then in the third one, which is not a decision problem but a promise problem, the problem says given a lattice basis B and a R from Q, the conditions are all the same. In the situation instances of S, that we have lambda 1 of L of B should be less than or equal to R. In no instances, that is, it's a Boolean value, promise value, yes or no. So we have to output yes only on the cases where lambda 1 of LB should be less than or equal to R, and on the other cases, no instances, lambda 1 of LOB should be greater than or equal to gamma times R. We are not insisting on getting the value on R itself. Now, the same story for CVP. So we have search gap CVP, which is you're scaling the thing with the gamma. Obviously, you have to find a closest lattice vector, which is closest by a factor gamma. Again, optimization and promise are the same as the previous thing. Now, shortest independent vector problem. That is, given a lattice basis B in Zm cross N, find linearly independent vectors v1, v2, etc. Vn such that norm vi less than or equal to lambda n for I less than. See, if the shortest independent vector problem is set on lambda 1, then that is equivalent to the shortest vector problem, because lambda 1 we have to find a v1 v2 with your v1 vn or v1 such that norm v1 less than or equal to lambda 1, which is the shortest vector. This is exactly the same as the shortest vector problem. But if we have two, then you have to find two linearly independent vectors v1 and v2 such that norm v1 and norm v2 should be less than or equal to lambda 2. That is the length of, or they should be considering the ith successive minima, the definition. That is, you have to find the lambda i's are the ith successive minima. You remember, I think. So lambda i's, we have to find n linearly independent vectors which are inside the closed ball of radius lambda n. That is the shortest independent vector problem. This also has an approximation variant, which is SAVP gamma for given gamma a function of n greater than or equal to 1. Given a lattice space is B, find linearly independent vectors v1, v2, etc. vn such that the norm of vi is actually less than or equal to the factor gamma n times lambda n for the same thing. There is a scaled up version of the or approximation version of the SIVP problem. Now again, I'm giving you another problem which is boundary distance decoding, which is again somewhere similar to the CVP again. So we are not doing too much on this. Now let us just starting a switch before let me introduce before I introduce learning with errors. Let me just tell you one thing. In cryptography, what we require is average case hard problem. That is, if you take a hard problem, any randomly chosen instance of the problem should be hard. That is our idea in cryptography. But all these problems which we have seen here are worst case hard problems. That is, there exist instances where the problem is hard, which is not an average case hard problem but a worst case hard problem. See, if you look at that in a such a maybe you can ask me back whether RSA is a worst case hard problem. Obviously, RSA requires average case hard problem, not a worst case hard problem. But the integer factorization problem is a worst case hard problem because only chosen instances will be hard. But RSA, sorry, integer factorization problem beyond some extent, beyond a particular extent, or if we put a threshold on the lower limit or lower bound, if we choose any prime numbers beyond that limit and multiply them, then that problem becomes an average case hard problem because given any random p and q beyond a particular limit, multiply them and give me back the product value, I won't be able to find the p and q value because it's a that makes it an average case hard problem because any random instance of p and q will give you a hard problem. Similarly here also svp cvp savp bdd, all these things will give you worst case hard problems, not average case hard problems. So we need average case hard problems. So there is a reduction from worst case to average case by Oded Rakev, which if you are interested you can read. The paper is available on archive and all. So we need average case hard problems for cryptographic requirements. So we are actually focusing on something like learning with errors. LW, let us just make a way for the problem. Let us start with LW distribution. So for a secret S in ZQ power n, the LW distribution AS chi. Chi is a error distribution over ZQ to the power n cross ZQ is sampled by choosing a uniform random vector A from ZQ to the power n and the error according to the distribution chi, producing the pair A, comma, inner product SA plus E modulo Q. Why that plus E? See, obviously it's a cakewalk if you know A and if you are having the inner product S comma A, you will be getting back S value. So if you know the matrix, suppose A is a matrix and we are having S comma A is another product of the matrix. So you just have to find A inverse and multiply it to that vector and you will be getting the value S. So it's actually a pretty cakewalk. If you don't do, or you can do, if you, or you can consider this as a equation form. If you are doing it as an equation form, considering A and SS vectors, and you are having components Xi's, then you will have this Gaussian elimination type of techniques to get the value of S back, provided E is not there. That is why we are adding the value of E there. Now we have again search LW and decision LW given randomly chosen samples AI BI. Maybe some are LW generated and some are randomly chosen. You won't be able to find a proper LW generated sample and you won't be able to distinguish between a randomly generated sample and a properly generated LW sample. So that is how decision LW works, and search LW, obviously given a LW sample you have to find S, the secret S. Now this is one case with the learning with errors. So we have crypto systems like Crystal, Skyber, and all those things which are the current cryptographic standards or the NIST standards which are currently available, which are mostly based on LW and the variants of LW which are ring LW, module LW, etc. So this is one important problem to see. Another problem will be SIS problem, that is short integer solution problem. Another hard problem which might you might find interesting if you have interest in cryptography in the post quantum setting. Now let us just look at another scenario, which is quantum cryptography. So, what do you mean by quantum cryptography? Quantum cryptography is actually something which is uh, implementable on a quantum computer. So, we have a quantum key distribution, that is, see, if you remember, if you remember properly, then what do we have? We have that a quantum key distribution or key distribution is the idea of asymmetric cryptography. So why do we need asymmetric cryptography? The question was, the asymmetric cryptography was used or is used to exchange keys for symmetric cryptography. So what if there is a quantum mechanical or quantum way of exchanging the keys? Now that is actually equivalent to finding a solution here using quantum computers. So exchanging the key using quantum computers, quantum key distribution. So we will actually share maybe a key derivation function or a key derivation input. A short shared key, we can make it to a large key stream. So we will be sharing a short shared key. We can make a large key stream out of it. So there are symmetric schemes which are stream ciphers. Somebody of you might have heard of that, somebody of you might not have. So stream ciphers are actually randomly generated bits which are equally lengthy as the message, which will be XOR to the message, and that is the idea. So it's a stream cipher is a classical version. It's not an analogous version of quantum cryptography, quantum key distribution, but a classical version which is kind of some kind of similar but not the same. So a stream cipher includes a mathematical function or a kind of operations on that, where QKD is actually involved based on physical techniques, and stream cipher is secure in any number of untrusted hops or any extension networks. So you can just go through that. So QKD requires a direct fiber optic connection. It's a very physical, because that is not a computation on a mathematical setting. So between involved hardwares, so stream cipher does not have any eavesdropping because it's actually incomprehensible. But QKD, there can be an eavesdropping, but eavesdropping or measuring actually interrupts the communication. Now in a stream cipher, it generates the gigabytes of stream per second in normal CPU, but it on QKD it requires obviously expensive special hardware, which is obviously referring to the quantum computer. Now let us look at one particular protocol. Uh, okay, now let me just go through a protocol which is BB84 protocol, which is a quantum protocol, which is again, we will be looking at a quantum protocol, quantum key distribution protocol, pardon me. So a measurement basis can be two types, a rectilinear basis and a diagonal basis. This you might have seen. Can you just somebody clarify whether we have seen this particular idea of rectilinear basis and diagonal basis of a quantum measurement and quantum computing? Can you just somebody say yes or no? Have you seen this? That's the question. Have you seen this idea of rectilinear and diagonal basis before? No, okay. Most of you haven't heard. So, okay, there is a question. How can cryptographic protocols and systems such as RSA and elliptical cryptography be adapted or replaced to ensure security against quantum computer-based attacks, which could potentially break current encryption methods? Okay, so that is exactly what I was talking about until now. See, the replacement is either lattice-based systems or any other hash-based or code-based or multivariate-based systems, which which we mentioned already. So RSA and elliptical cryptography, which are seeming to be vulnerable, because elliptical cryptography also involves elliptical discrete logarithm problem, which is again vulnerable when sufficient quantum computer will be there. So we have to replace these things. I told you already. We have to re-encrypt it using some post-quantum algorithms, or we have to maybe switch as soon as any further communication which we are doing should be based on these post-quantum standards. That is the idea. Hope you have an idea. If not, I'll finish and we'll just have a, conversation about that post this discussion. Okay, now back to the thing BB8 for protocol. There will be a rectilinear basis and a diagonal basis. Obviously, from the figure, you can see the blue one shows a diagonal basis. Obviously, they are showing a diagonal fashion, and the other is a rectilinear fashion. So, this is the polarization. So, in a rectilinear basis, the x axis or the horizontal axis shows 0, while the vertical axis shows 1. And in the diagonal thing, the main diagonal shows 0 and the off diagonal shows, sorry, main diagonal shows, so let's just put this diagonal and anti-diagonal. So diagonal shows 0 and anti-diagonal shows 1. Now, if Alice wants to communicate something to Bob, suppose Alice wants to communicate something to Bob. Alice is choosing a bit string 100101001, and Alice encoding basis rectilinear, diagonal, rectilinear, diagonal, rectilinear, 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 and diagonal. So that is what Alice chooses. Now Alice is having a, for obviously, 1 in rectilinear basis is vertical, not horizontal. So it will be V, and 0 in diagonal is D, not anti-diagonal. 0 in rectilinear is horizontal. 1 in diagonal is anti-diagonal. Sorry, 1 in diagonal is anti-diagonal. 0 in rectilinear is H. So you can see this H. 1 in rectilinear is V. 0 in rectilinear is H, 0 in rectilinear is again H, 1 in anti-diagonal is, so diagonal is A. So this is all Alice encoding basis and Alice polarization. Now Bob is using some measurement basis here. See, Bob is using the same basis as A in this case, but he don't know. He is randomly picking a basis. So he is using this basis, he will be getting the same V, because when he measures, he will be getting 1. But if this is done encrypted in a encoded in a diagonal basis, and Bob is using a measurement basis which is rectilinear, he might get V or H. We don't know, but in this case he got V. Anyway, he got 1. For the third one, Alice is using the thing H, but Bob is using a different basis, which is diagonal basis. So he got a D value. Randomly, D or A can come. He got D value, which is 0, which is the same as the one which he sent. But that's a catch. There's a catch there. I'll come to that. And again, in the fourth one, again, different basis, different values, value changed, different basis, value changed. Here, same basis, same basis, same basis, same basis, all the same. Now, after doing this particular, completing this process, Alice and Bob will publicize their bases, not the values, but the bases. So, Alice says, I am using the basis plus into plus into plus 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 into, and Bob says plus plus into plus 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 into. So now Alice and Bob can say that Alice and Bob agreed on the basis on the first case, fifth, sixth, seventh, and eighth. So they will only choose the vectors 1, 5, only the bits 1, 5, 6, 7, and 8. Okay, again a question. What are the practical limitations and potential vulnerabilities of the BB84 protocol in real-world implementation, particularly with regard to photon loss, detector efficiency, and eavesdropping attacks? Definitely there are, see, first of all, it has to be implemented. It's only on papers right now. So practical limitations means we have to code it on kind of a simulator, at least on a simulator or a real quantum computer. Obviously, the first is the choice. So we have practical limitations, but it's not completely exposed yet. Obviously, photon loss and error creeping is one basic, and obviously measurement. See, this is an ideal case which I am referring to. This is an ideal case where the measurement can be done without any error. So here also in this case, even though they are using same basis in first, fifth, sixth, and 1, 5, 6, 7, and 8 cases, there might be an error. So we can't guarantee anything on this thing. So anyway, back to the thing. 1, 5, 6, 7, and 8 are the bases which are found to be similarly used by Alice and Bob. So they will be choosing the first bit, fifth, sixth, seventh, and eighth. So they will be choosing 1, leaving the rest for 11001. That is the bit string which they will use to create the long. See, this one we have seen that large key string. Short shared key will be 11001. that will be used to make a large key stream. Even though there is a similar value in third case, they won't be taking it because the measurement bases were different. So they don't even know whether that is same or not. They don't even bother. Only when the measurement bases are the same, they will be doing it. So that is the basic idea about the communication using BB84 protocol. And thank you. Any questions? You may now unmute and ask if you have any questions. Hello, did I lost you? Ma'am, Jamie ma'am, are you there? Hello. Hello. Any questions? Anybody? No, no, no. I mean, you are listening. I know I'm asking for the questions. Okay, I have question. Example is nice, but mathematically speaking, can you tell me the generator of rectilinear basis and diagonal basis? See, the same thing. Like there is no gen. See, this is not a regular mathematical basis. So, Doctor Anu, I mean, I think you are from math background. So, since we were talking about lattice basis until now, I mean, are you confused with? I mean. Dr. Anu, can you just unmute, like, if you're okay with it? So, are you from a mathematical background? Yes. Okay. So the idea is, since we were talking about basis and dimension and all those things in a linear algebraic perspective, in the case of lattices, that need not be. I mean, that's a wonderful question. I thank you first of all. So that need not be confused with the basis here. So the basis here does not mean any mathematical basis or linear algebraic basis. It does not have any connection between that. So this is a measurement basis, like a scale, kind of a measuring instrument. Here basis refers to a measuring instrument. So we can either measure something using a rectilinear scale or a diagonal scale. So if you are like, suppose you are, say the same example as a photon. If you are sending it through a slit which is made in shape of a plus sign, then obviously you have to get the plus sign on the other side, or you have to keep the plus sign on the other side to get it correctly. But if you are putting the into sign or a multiplication sign on the other side, you won't be getting the value correctly. So that is a different kind of measuring scale used by either parties. So if you and your other party partner, communicating partner, uses the same plus kind of scale, then they will be actually having the same value communicated to each other. But if they are using the different scale, then that measurement actually spoils the thing and actually loses causes the photon to lose the superposition state, and that actually leads to loss of the thing. So we won't be considering that in this particular scenario. The bits 2, 3, 4, and 5 are yeah, 2, 3, 1, 2, 3, 4, and 5. Yeah, 2, 3, 4, and 5 are not considered only because of that particular reason. So don't please confuse with the measuring basis with the normal linear algebraic basis. Is that clear to you? Shall I explain anything more? Thank you. It's clear to her. Okay. Or him, I don't know. Uh, Again, somebody has asked for a link, maybe for the feedback form. See, informally speaking, let me tell you this, it is too much heartbreaking to see that you are not worried about the content but the feedback form. because it takes a lot of pain and effort to make a content for an FTP. Hope you guys are making use of it, and maybe when you are taking an FTP as a resource person, you might know. Maybe you.
Sir, 1 minute, 1 minute. So I'll just address the participants. Participants, do not post any message in the chat box. We know the time at what time we have to send the feedback link. Past 5 days, we have sent the feedback link after the end of the session. So kindly wait and stay back and listen to this session because it's hard effort and Arvind sir also spending his valuable time here in addressing you. So kindly listen to this session and do not post any kind of this messages in the chat box. Kindly cooperate. Arvind sir.
Yes, ma'am. There's a question. Can you share the PPT? The PPT is actually available with the coordinators. Ma'am, Jemima ma'am is having the PPT already. She will be sharing it with you because I don't have any option to share it with the group. The organizers will.
Sir,
Yeah.
sir, 1 minute.
Yes,
Till
ma'am.
yesterday, all the sessions PPT I have posted in the drive. In the same way, at the end of this session, I will share this PPT as well. So do not post such kind of messages in stopping the resource person and kindly interact with the resource person with your technical queries.
Okay, we have a question. Kindly suggest us some books to understand quantum cryptography from the mathematical view. The problem with suggesting a book is that, Dr. Anu, the issue is that I don't actually have access to any particular kind of a book which I can suggest, because which I can say standard. I am actually referring to research papers, and I am actually making use of the kind of idea about the Hilbert space kind of idea I'm actually using to connect between mathematics and the quantum computing. So the more than the linear algebra perspective, I'm actually concerned about I'm actually worried about the operator algebraic perspective, considering that von Neumann algebra kind of like objects in the quantum setting. I'm actually looking forward to, and research papers connecting them I'm using. I don't actually have I mean, there are books. I'm not saying there are not no books. I'm not confident enough to suggest any books which I can say this is a proper study material. Apologies, I don't have any kind of suggestion on that, but I recommend that if you are mathematically keen on that, please try to read connection between Hilbert spaces and maybe von Neumann algebra or operator algebra and the quantum states or quantum cryptography, quantum computing. Then you will be able to understand the idea about these things. So suppose if you want to learn about quantum cryptography, obviously there are only very few like protocols like BB84 and the entanglement based E91 protocol. Very few are there, so you can just go through the papers itself to get an idea about that. But for post quantum cryptography, if you can just go through the book by Dan Bernstein, or maybe Dan Bernstein's book is some kind of advised, but will be of a standard reference. If you know cryptography, you can follow that. And another question, BB84 uses 4 quantum states to encode. Because of this, it is efficient over other. No, 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 ma'am. Actually, sir, actually, Dr. Lakshmikant. So the BB84 uses 4 quantum states to encode. So this is the first one which was published. There are actually other efficient mechanism, because it did not use any entanglement here, right? So we have actually entanglement, quantum entanglement, and quantum superposition based other schemes which came in the early 90s itself. So this is one kind of or one particular kind of encryption algorithm or a key distribution algorithm which was aligning with our topic. That is why I mentioned, because this is easy to understand and kind of like for a beginner level this will be easy. So if you want an intro or just a stepping stone, this will be useful. So you can actually have a research further. It's fine, completely okay with that. But BB84 is not a standard. BB84 is a just a beginning thing. It's not a standard. It's not a kind of like the best thing. Thank you for the wonderful questions. I appreciate all those things. So, any other questions? Anybody? Any questions? So you can actually, if you are interested, you can reach out to me with my email ID. I'll just I think I don't have that right now. Okay. I'll may I, I'll type my email ID in the chat box. So if you want any uh, if you have need any queries, you can just email me. Yeah. So I have my email ID typed in the chat box, so you may get that. Jimmy Mama, please share them my email ID as well, because sometimes they might not see the chat box. So the interested people might be. I mean, you can communicate to me. You can write to me. I'll be happy to help. We can even collaborate if you have a interest in that. So sir, can you please suggest some research topics in quantum cryptography? Obviously, quantum cryptography is a hot topic, research topic. But again, Shelley, Shiju, George. So the question is kind of ambiguous. Let me address both the part of it. So quantum cryptography, which involves two parts. If are you referring to quantum cryptanalysis or the quantum cryptography? See, the making and breaking systems are there. So there are two ways. I told you. So in a constructive fashion, there is a cryptography. There's a destructive fashion of quantum cryptography. So which we discussed in the beginning. So if you are bothered about the like depending on what, so you can focus. So you can actually try to find or better or find algorithms which are derivatives of sure or independent algorithms which can be tracked, which can be used to break the crypto systems, or you can make them, or you can adapt to them, or these are the research areas on destructive side. And on the constructive side, you can actually look again. There are two subdivisions. You can actually make quantum key distribution schemes, which are to be implementable on quantum computers. You can make them error free, or you can choose the existing schemes and optimize them for better performance. That's one option. Then you can actually choose the mathematical way depending on your background. The mathematical way of addressing this thing, mathematically you can just go for and make a lattice base or some other hard problem which is intractable to a quantum computer. You can just make that. So these are the possible research topics or research ideas in quantum cryptography. Can you share your contact number and give a broad idea of research scope in quantum computing? This is already mentioned about the research scope. Obviously, it's a hot topic. You can just do that. And contact number, and I mean, you can just get the email ID from ma'am, or I have typed that email ID, or I mean, I don't have the email ID right now with me. I mean, to screen to share. It's there in the chat box. You can just get that. Uh, can we get this presentation video? Obviously, this is available with the PPT will be available with the ma'am. She will be sending it. Okay. So, any other questions, anybody? The question to Hasina A, please send feedback link. I have seen your question before also. So you are actually, I think you are coming once in a half an hour and asking for the feedback. You have not listened to whatever we are mentioning in between. Anyway, I appreciate your presence here.
Kindly stay back. Don't disturb in between. We are in the end of discussion.
Yeah, so I get some wonderful questions. I am actually very much pleased to get these questions. So again, Dr. Prashanti has raised the hand. So
Yes, sir. I have. She is supposed to unmute from her end.
okay, okay, maybe again a mistake. So you can. I mean, I think they have access to the chat box, right? Everybody has access to the chat box.
Yes, sir.
So my email ID is in the chat box. ss underscore Aravind Vishnu at cb.amrita.edu. ss underscore Aravind Vishnu at cb.amrita.edu. So
Sir,
you
if you
can.
select every one option,
Yeah, I
then
mean,
it.
I put a message there.
Okay, sir.
So you can just look at that. So it's fine with that. So if you need, you can just get it from ma'am or get it from the chat box. Our website is under construction, so it will be up soon. Or I mean, you can get my contact information from the website also. So, but the website is actually down right now. It will be up within a month, so you can just get it from there also. And you can connect me over LinkedIn or any other platform if you want. I mean, anyway, any kind of academic research helps can be offered if it is a genuine request. So it's wonderful sharing time with you. So I don't think any more questions are there. People are worried
Mhm.
about LinkedIn IDs. You can search for Aravind Vishnu, and you can search with my institution name, Aravind Vishnu from Amrita Vishwa. You can get that. Okay, so
So shall
ma'am,
we wind up
yeah,
this?
obviously, ma'am. So I don't think any more questions will be there. So we can just wind it up.
Okay, sir. We are truly honored to have Dr. Aravind with us today, sharing his valuable insights on cryptography in the quantum field. His dedication to advancing knowledge in this domain is inspiring, and we sincerely appreciate you, sir, for taking the time to share your expertise with us. Thank you, sir, for your invaluable contribution to our learning journey. Thank you for sharing your expertise and inspiring us to explore this domain further. Thank you so much, sir. Thank you.
Thank you so much for the opportunity. Thank you all
Thank
for the attendance.
you. Thank you, sir. Thank you. Sir, you can disconnect.
Okay, ma'am. Thank you.
Participants, you can enter your attendance now. The feedback link is shared. Tomorrow's agenda, I have sent it to your mail as well as I have posted in the WhatsApp group. The session will start at 2 o'clock, and you have to join here for getting the feedback form as well as for tomorrow's attendance as well as the test link from this session. So you have to join in this webinar link for knowing your attendance and knowing your test link. And I won't share these two in any other medium. Okay, so you have to join in this webinar link sharp at 5 o'clock. So 5 to 6 is the timing for you. You can take your test at any point of time. 5 to 6, the link will be open. Test link will be open from 5 to 6. And the test link will be posted here. You're not going to take the test from the ATAL login or anywhere else. So you have to come and join in this webinar link. And here we will share the test link as well as the attendance link for day 6. I hope you all have got it. I have posted the agenda. As per the agenda, exam time is 5 to 6. The link will be on. Test link will be posted in this webinar. So you have to join here using the same webinar link, and your test link, attendance link for day 6 will be posted here only. So you have to join by 5 o'clock. So before that, we have 2 sessions. So you have after the completion of that 2 sessions only, exams will start. So kindly join for the afternoon session by 2 o'clock. We have 2 sessions, and after that we have exam, and then you have to join for the validity function. The validity function is just for 15 minutes only. So I request all of you to join here. Any other doubts, please post it. The materials also shared in the WhatsApp group. If you have any doubts, you can post it here. How many questions? Once you open the questions only, you will know, ma'am. So it is an MCQ based questions only, multiple choice assessment through ATAL. WhatsApp group link, you can check in the first email communication that you have received from me about this webinar link. In the same mail only, based on your ID number, which WhatsApp group you have to join. Two WhatsApp groups are there. So I have mentioned ID number from 1 to 250 in WhatsApp group 1, ID number, the remaining ID numbers in WhatsApp group 2. Materials already posted in the WhatsApp group. Attendance form. Kindly fill your attendance for today's session. There is only one feedback form today. Kindly mark your attendance. Don't miss your test on tomorrow. It is from 5 o'clock. So that's why I have sent it by WhatsApp and email. Kindly join. If you have any queries, please post it here. Attendance form. Tomorrow session starts at 2 o'clock. We have 2 sessions followed by exam and then valedictory. You can join in the WhatsApp group. Once again, I'll post the materials link. Those who joined late also should know the materials link. So once again, I'll post it. No need to go to ATAL portal, only here only. You have to join here. It's a Google form based MCQ test one. Everything is through here. Yes. No need to go to ATAL portal. During the test time, 5 to 6 p.m., I'll be here online. Even though when you take tests, I'll be here online. Any problem or any doubts, you can report it here. Kindly send the materials. Yeah, at least by tonight. Once again, I'll share. Then only those who joined late in the WhatsApp group can also get benefit. What time does the test link expire? 6 o'clock sharp. 5 to 6, 1 hour it will be. So within the time, you can take your test. Test link generate in chat box. Yes, test link will be posted in the chat box only. But 5 to 6, I'll be here in case in between. If you have joined also, if you ask, I will post it once again. But 5 to 6 only, the test link will be joined at any point of time. In case of your travel or any other problems, you can come here and join. Don't miss the test. 5 to 6 online, I'll be available here. You can ask or post a message in the chat. I will share the link here. I cannot share the link through WhatsApp. I can post the test link through this webinar. It WhatsApp group, ma'am. WhatsApp group link, you can check your first mail that you have received from me about this webinar link. I have sent it to you. So same mail, when you go back, you can able to find out in the body of the mail, you can able to read WhatsApp group 1, WhatsApp group, any one WhatsApp group based on your ID number, please join. Have to complete the 41. Okay, yes. Yeah, that also I'll inform. Sure, sure, sure. Thank you for the information. When we will get the certificate and from where? ATAL, from the ATAL portal only you can download. We have to enter your attendance over there. We have to upload your feedback details, what we have collected from here, everything once we have uploaded and submitted. And your test marks also we have to upload there. After that, the certificate will be enabled. Which criteria is for certificate? You have to gain the minimum mark is 70%. You have to get it. Attendance 80%. Minimum requirement for certificate Attendance 80%, minimum requirement I'm saying, okay, attendance 80% and marks 70%. Kindly send ma'am link. Those who joined late, kindly mark your attendance. Don't miss. Tomorrow, 5 to 6 p.m. you have test. Test link will be posted only in this webinar. So please come and join. And through the chat box, you can get to know you. So within 2 to 3 days, we will get certificate. I'll update you tomorrow about how to get the certificate, all other instructions, ma'am. Till tomorrow, what are the instructions are there, I'll push. And after the end of tomorrow's session, I'll update you what are the things from your end you have to do for getting the certificate. I can start the exam by, could you please leave the expiry time? No, 6 o'clock sharp, it is supposed to be closed, and 6 to 6:15, you can complete your test. If you join by 5:30 also, you can complete your test. No worries, ma'am. So, so that the exam can be completed without anxiety. Don't worry. Definitely, you can able to complete the test. You have enough time. I didn't, well, yesterday session. No, yesterday session's feedback form will not be shared here because of any other problem. Only today's attendance. My college only ended at 5. So that is why I'm saying 5 to 6 o'clock, the test link will be available. 5 to 6. So anywhere while you do during the travel time also utilize the time. The thing is you have to come and join in this webinar link and take your test link and you can attend this test and you can finish it. This is the time given by AICT ATAL Academy as per the instructions we are working. They have given the schedule at what time it is supposed to be conducted. So kindly cooperate. No, we are not. We are not supposed to close it. It's informed 5 to 6. Feedback form. Those who joined late. Okay, that's all for today. I hope you all have entered your attendance. I'm closing this meeting. Send me the materials. I joined late. The materials I have posted in the WhatsApp group. Kindly check. And in case if you didn't join WhatsApp group, you go to your first mail communication received from me. There I have mentioned the link for joining the WhatsApp group based on your ID. So there are 2 WhatsApp groups are there. Based on your ID, you join in that particular group, you will get the materials. Once again, I'll post the material at the end of this meeting. At the end of this meeting or after or within this day, I will post the link once again. Morning also, I'll try to post it one more time. I'll repeat. Nobody should. I joined late and how to make the attendance percentage as 80. You have to attend all the sessions, sir. Then only you can get attendance percentage 80. Thank you, ma'am. Okay, I hope your doubts are cleared and I have communicated the agenda for tomorrow. Tomorrow's session starts at 2 o'clock and we have 2 sessions followed by exam and then valedictory session. Exam link will not be opened so after 6 o'clock. So 5 to 6 is the time for giving your test. Thank you. Okay. Utterance link. Now only you're coming back. Send the attendance link. Kindly join at the sharp time for tomorrow's session. So follow the agenda. What will be the time of exam? It means you have joined just now. Sam Lita. What will be the time of exam? Ma'am, are you in the WhatsApp group or no? Are you in the WhatsApp group? So please join in the WhatsApp group. And are you getting mails from me? Sam Delat. In the mail also I have communicated. WhatsApp group also I have posted the agenda about tomorrow. What time is the exam? Okay, 5 to 6. 5 o'clock sharp, you have to join in this webinar link. Here in the chat will be posted, uh, uh, a test link will be posted here. I'll be in online from 5 to 6 till the end of validity section. I'll be here from 2 to 6:15. I'll be here only. So if you have any doubts, if you post it in the chat box, I'll ready to answer. Okay. Don't worry. Maybe you are in travel, but don't miss this exam and don't miss tomorrow's sessions as well. Thank you all. Attendance link. Now only joining. Are you left in between? I don't know. Kindly go through the instructions for tomorrow in the WhatsApp group as well as in the email. Can we get the certificates? Certificates you have to download from the ATAL portal. Once we have updated the attendance, feedback, and your marks over there, then you can able to download your certificates. But you have to secure 80% minimum attendance and 70% marks. Then only your attendance, your certificate will be generated in the ATAL portal. Any other doubts? No. Okay, thank you all. I'm closing this meeting.